Welcome to the third lecture of module 4. In the previous lecture, we have discussed the absorption towers. Packed and plate towers are used for absorption, and we have started with the steps to be followed for design of packed towers. And some of the design procedures are discussed previously, and we consider design of packed towers by individual mass transfer coefficient method. In this lecture, we will discuss packed tower design by overall mass transfer coefficient methods and also by height of transfer unit methods. So, let us consider packed tower design based on overall mass transfer coefficient method. Now, if we express the overall flux Na is equal to capital Ky into y minus y star. Capital Ky is the overall mass transfer coefficient for the gas phase, and then we can write dz is equal to minus g dash dy divided by capital Ky A into 1 minus y into y minus y star. Y star is the gas phase concentration in mole fraction which is equilibrium with the liquid bulk concentration x. Now, the required packed height we can obtain by integration of this equation. So, z would be equal to integral 0 to z dz would be integral y2 to y1 g dash dy by capital Ky A 1 minus y minus y star. So, now this integration can be done either graphically or numerically. So, for graphical integration we can follow the procedure First, plot the operating line and then take any point x y on the operating line then we can draw a vertical line through this point on the operating line and extend up to the equilibrium curve. Which meets at a point y star. For a set of values of x y, we can obtain a set of x star y star, and then we can obtain the value of the integration. So, now we will consider another method which is packed our design by height of transfer unit. We know that y minus y I is equal to 1 minus y I minus 1 minus y. So, y I b m is the log mean concentration gradients. We can write is equal to 1 minus y I m is equal to 1 minus y I minus 1 minus y divided by ln 1 minus y I divided by 1 minus y. Y I b m is equal to logarithmic mean of 1 minus y I and 1 minus y. Now, we can calculate the height of the packing z. We can write z is equal to integral y2 to y1 g dash 1 minus y I m dy divided by small k y a into 1 minus y I m into 1 minus y minus y I. We can define the height of transfer unit. Height of transfer unit we can define HTG is equal to G dash divided by K y A 1 minus y I m. We can, this will be G dash divided by K y dash A. So, this equation of Z we can write Z is equal to G dash by K y A 1 minus y I m integral y2 to y1 1 minus y I m dy divided by 1 minus y into y minus y I. So, this we can write HTG integral y2 to y1 1 minus y I m divided by 1 minus y into y minus y I. The integral of this part can be termed as or defined as NTG. So, NTG is equal to integral y2 to y1 1 minus y I m by into dy divided by 1 minus y into y minus y I. Therefore, Z is equal to HTG into NTG. So, this is the equations of packed height in terms of height of transfer unit and number of transfer unit. Now, this relationship we can apply for liquid concentrations as well. So, for liquid concentration we can write the counterpart of this equation is equal Z is equal to HTL NTL. So, HTL is defined as is equal to L by K x A into 1 minus x I m, and NTL can be written as integral x2 to x1 1 minus x I m divided by 1 minus x into x I minus x into dx. So, HTL is basically height of an individual liquid phase transfer unit. And NTL number of individual liquid phase transfer unit, liquid phase transfer unit. So, this is in terms of the liquid phase concentration of the species, we can define the height of turns per unit and number of turns per unit, and then we can calculate the packing height. Now, for some cases the equilibrium distribution curve is straight and the ratio of the mass transfer coefficient is constant. Z is equal to N T O G into H T O G. So, where Z is equal to integral y2 to y1 g dash into 1 minus y star m dy divided by k y a into 1 minus y star m into 1 minus y into y minus y star. This we can write g dash divided by k y a into 1 minus y star m integral y2 to y1 1 minus y star m dy divided by 1 minus y into y minus y star. So, this part is known as HTOG and this is NTOG. So, this is based on the overall mass transfer coefficient. HTOG is equal to height of an overall gas phase transfer unit which is equal to g dash divided by k y a into 1 minus y star m, and NTOG is equal to number of overall gas phase transfer unit which is equal to integral y2 to y1 1 minus y star m dy divided by 1 minus y into y minus y star, and 1 minus y star m is equal to log mean concentration gradient 1 minus y star minus 1 minus y divided by ln 1 minus y star divided by 1 minus y. Let us take an example to calculate the pack tower height. We will consider the similar example as we considered in our previous lecture, and in this case the value of all the parameters remains almost similar. As we can see, the equilibrium data is also same for the system, and this is a pack towers is to be designed to absorb 95% of sulfur dioxide from an air SO2 mixture using pure water. The entering feed gas mixture contains 15 mole percent sulfur dioxide and 85 mole percent air at 303 Kelvin and 101.3 kilopascal total pressure. The feed gas rate is given 1000 kg per hour. The solvent rate is also given 30,000 kg per hour. The tower cross sectional area is 1 meter square, and it is given that K dot X A is 1.1 K mole per meter square second mole fraction, and K dot Y A is equal to 0.07 K mole per meter cube second in mole fraction. Calculate the tower height using height of turns per unit method. So, the last method which we have discussed, we will follow the similar procedure. Here this is the packed towers, and all the symbols as we discussed earlier in the derivations are remain same. So, now we will calculate the average molecular weight of the feed gas. Average molecular weight of feed gas is equal to 0.15 15 mole percent into 64 plus 85% is air into 29. So, this will give 34.25. Then total feed gas rate, we can calculate, which is given 1000 kg per hour, which is equal to 1000 divided by 34.25. This will be kilomole per hour. So, this is equal to 29.2 kmol per hour. This is we can define as G1. This G1 is 29.2 kmol per hour. Now, feed concentration is given. Feed concentration is equal to 0.15 mole fraction, that is this one 0.15. So, we can calculate capital Y 1 is equal to 0.15 by 0.85 is equal to 0.177. This is mole ratio. Now, the feed gas rate on solute free basis we can calculate. Feed gas rate on solute free basis. So, that is G s is equal to G 1 into 1 minus Y 1, which is equal to 29.2 into 1 minus 0.15, which will give 24.82 kmol per hour. And the entering SO2 is equal to G 1 y1, which is equal to 29.2 into point y1 is 0.15. So, 15 which is 4.38 kmol per hour. Now, 95% of entering sulfur dioxide is absorbed. Then SO2 which is absorbed is equal to 4.38 into 0.95 is equal to 4.16 kmol per hour. So, this is the amount absorbed. So, the amount leaving from the tower, SO2 leaving is equal to 4.38 minus 4.16 kmol per hour. So, which is equal to 0.22 kmol per hour. Now, we can calculate the gas phase concentration at the exit. Y2 is equal to 0.22 by Gs is equal to 0.22 by 24.82, which is equal to 0.0887. Similarly, Y2 will be capital Y2 by 1 plus Y2, which is equal to 0.00887 divided by 1 plus 0.00887, which is equal to 0.00879. So, this is the exit concentration 0.00879. Okay. Now, we know that LS is given 30,000 kg per hour. So, which is equal to 30,000 by 18 kmol per hour. This is the pure water rate, which is equal to 166.67 kmol per hour. Gs we have calculated, Gs is equal to 24.82 kmol per hour, and Y1 we know that 0.15, Y2 is 0.00879, and X2 is also known, which is 0. The entering solvent is pure water. So, X2 should be 0. Gs into Y1 by 1 minus Y1 minus Y2 by 1 minus Y2 will be Ls into x1 by 1 minus x1 minus x2 by 1 minus x 2. Now, if we substitute, we know all the parameters except x 1. X 1 is unknown. So, if we substitute this parameter, it will be 24.82 into 0.15 divided by 1 minus 0.15 minus 0.00879 divided by 1 minus 0.00879 is equal to 1666.67 into x 1 by 1 minus x 1 minus 0. So, from this we can calculate x 1 would be 0.002496 minus 0.002496 x 1. So, from this x 1 1.002496 x 1 would be 0.002496. So, x 1 after solving it will be 0.0249. So, this is the concentration of SO2 in the exit liquid stream. Now, if we use the method of overall height of transfer unit to calculate the packing height, we know that Z is equal to H T G into N T G. Okay. So, H T G is equal to G dash by K y dash A, and N T G is equal to integral y 2 to y 1 minus y I m divided by 1 minus y into y minus y I dy. Now, let us calculate HTG. Calculate HTG, which is equal to G dash by K dash y A. We know tower cross sectional area. Is 1 meter square. Now, we will calculate G 1 dash would be G 1 divided by tower cross sectional area, which is equal to 29.2 divided by 1, which is equal to 29.2 k mole per hour meter square. Similarly, G 2 dash we can calculate G s divided by 1 minus y 2 into cross sectional area, which is equal to 24.82 divided by 1 minus 0.00879 into 1, which is equal to 25.04 kmol per hour meter square. Now, if we take the average of these two, that will be your average G dash over the tower. Therefore, G dash will be G 1 dash plus G 2 dash by 2, which is equal to 29.2 plus 25.04 divided by 2 is equal to 27.12 kmol per hour meter square. It is given that K y dash A is 0.07 kmol per meter cube second mole fraction. So, we can convert it to 0.07 into 3600 kmol per meter cube hour mole fraction, which is equal to 252 kmol per meter cube hour mole fraction. So, now HTG we can obtain 27.12 G dash divided by K dash y A, which is 252 is equal to 0.108 meter. This is HTG. Now, we will calculate NTG. NTG, we know that it is equal to integral y2 to y1 into 1 minus y I m divided by 1 minus y into y minus y I into dy. Now, we have to evaluate this integral. Then, to evaluate this integral, we need to know the interfacial concentration. Interfacial concentration. As we followed earlier, we will follow similar procedure. First, we will plot the equilibrium line. Plot equilibrium line on xy plane, and then plot the operating line. So, this is the equilibrium data which are given x and y, and this is the equilibrium curve, and this is the operating line curve. Based on the data given, we can locate any point at this location, say n, and this is x y on the operating curve. Then we draw a line from this curve with a slope is equal to minus k x dash a divided by k y dash a, which is equal to, as per the given value, is 15.71, and from this point we plot a curve with that slope which will meet in this point as at S, and this S point you will get this is x I and y I, and this is the first approximation S x I y I. This is the first approximation of the interfacial concentration. Then the true value can be obtained by plotting minus k x a by k y a with the slope of this, and which will meet at some point on equilibrium curve. Now, minus k x a divided by k y a is equal to minus k x dash a divided by 1 minus x I m divided by k y a dash divided by 1 minus y I m. So, which is equal to minus 15.71 into 1 minus y I m divided by 1 minus x I m. So, point N is the upper terminal point. N we considered in the previous one is the upper terminal point. So, the value at this point is x is equal to 0.00249 and y is equal to 0.15. So, if we plot with the slope of 15 minus 15 point from this point minus 15.71, then it will meet at point S. Here x I and y I, the value of x I y I is equal to at S x I is 0.0036 and y I is equal to 0.14. So, with these values we can calculate k x a and k y a. Now, we can calculate 1 minus y I m is equal to 1 minus y I minus 1 minus y divided by 1 ln 1 minus y I divided by 1 minus y. So, if we substitute, it will be 0.855, where y I is 0.14 and y is equal to 0.15. Now, we can calculate 1 minus x I m, which is 1 minus x into 1 minus x minus 1 minus x I ln 1 minus x divided by 1 minus x I. So, the values of x I is 0.0036 and x is equal to 0.00249. If we substitute, this will be 0.997 minus k x a divided by k y a is equal to minus 15.71 into 1 minus y I m divided by 1 minus x I m. After substitutions, this will be minus 13.5. Now, if we start from point n, which is equal to 0.00249, that is the upper terminal point 15 with slope minus 13.5 will give the true value which meet at S 1. So, the meeting point would be at S 1. Suppose from this point it meets some nearer to this point S 1, which is new x I y I. So, this S 1 is 0.0036 and 0.141. Now, set of say x y values, we obtain set of x I y I. So, this is shown in this table. We have different y values and we have y I values, and we have calculated the difference, and then we have calculated the integral term. If we plot this versus y, this is basically 1 minus y I m divided by 1 minus y into y minus y I. So, this is in this axis and this is y. So, if we plot this, then it will give the value area under the curve, which is NTG. So, area under the curve is equal to 18.05. So, NTG is equal to 18.05. So, packing height which is Z is equal to HTG into NTG, which is equal to 0.108 into 18.05 meter, which is coming about 1.95 meter. So, this is the method by which we can calculate the packing height required for a particular operation. Thank you.